Greetings everybody. So today we are going to discuss about our new topic, which is solutions. Giving the introduction, what are solutions? Firstly, we need to understand what is a phase. Phase is basically a property. Phase is a state in which two or more than two substances, in which any substance or a mixture is having fixed properties and fixed composition at constant temperature and pressure. So at that condition we call it as phase. Let's suppose water. Water is there. Water basically at liquid state at constant temperature and pressure will have constant properties and fixed composition. So it would be having a single phase. Likewise, if we talk about if we mix water with NaCl salt, so at that moment it will cause to produce a mixture, a homogeneous mixture. It will cause to produce a homogeneous mixture, and that homogeneous mixture will have a fixed composition of salt and fixed composition of water, which will indicate that fixed composition of salt and fixed composition of water being presented in that, which means uh, in all proportions all of the salt will be having fixed properties and fixed composition, so they would be considered in a single phase, and at that moment it would be having homogeneous mixture, which means it's in a homogeneous mixture it will be having a fixed composition of that salt, which means in all of the sides, in all of the portions of the container there will be equal amount of salt and water, right? So in that case that would be considered as a homogeneous mixture, and that homogeneous mixture of two or more than two different ionic or molecular substances with respect to the single phase, homogeneous mixture of two or more than two different ionic or molecular substances in a single phase is known as solution, right? This is on a solution. What are the characteristics of solution? Solution basically it is considered to be made up of two parts, solute and solvent. Solute, solvent. When it comes to the solute basically it is the part which is to be dissolved, and solvent is the part which is the dissolving substance. Solute is smaller in amount, solvent is larger in amount. Solute basically uh, is dissolved in the solvent, and the amount of solute dissolved per unit decimeter cube of solvent, amount of solute dissolved per unit decimeter cube of solvent or per unit decimeter cube of the solution is known as the concentration of the solution. Concentration of the solution, and that concentration of solution is measured in mole per decimeter cube, right? This is measured in mole per decimeter cube. And one more thing that I would like to highlight over here is about uh, the characteristics. So characteristics are in such a manner that here solute is solution, generally solution is having, first and foremost, it does not allow light to pass through it, so it does not follow the Tyndall effect. This is known as Tyndall effect, that light is not able to pass through it. Light is not able to pass through it, right? So it is a Tyndall effect is occurring in it. Moreover, um, it cannot be separated by physical methods, although it is combined together by physical methods. Salt is combined together by physical methods, not by chemical reactions or chemical methods. So even though it is combined by physical method, it cannot be separated by filtration. It cannot be separated by filtration, right? After that, salt is, it is having, the particles of salt are less than 1 nanometer, less than 1 nanometer. Okay. After that, particles of salt are less than 1 nanometer, Tyndall effect occurs, and filtration. And other characteristics of salt are solvation energy. The ability of salt to dissolve solute into the solution, the ability of solution to dissolve into the solute into the solution is known as solvation energy. Now, solvation energy is inversely proportional to lattice energy. We know that what is lattice energy? It is the amount of energy which is required to dissociate the ionic salt into its ions, or form the ionic salt uh, from its gaseous ions or aqueous ions. So lattice energy basically here, um, it is considered to be having binary ionic compound. Lattice energy of binary ionic compounds. Lattice energy of binary ionic compounds is there. Lattice energy of binary ionic compounds, and that is basically inversely proportional to the solvation energy, which means if we talk about lattice energy is increased more amount, it will be more difficult to dissociate the binary ionic salt into ions into the solution, due to which it would be difficult, more difficult to dissociate the ions into the solution, due to which the ability of the solute to dissolve in the solution would be decreased, due to which the solvation energy would be decreased. And in that case, as solvation energy is decreased, we can also consider the hydration energy to decrease as well if it is case of water. So in case of water, the hydration energy would be decreased as well. Hydration energy is decreased. And if we talk about such case in which lattice energy is higher, lattice energy is higher in case of lattice energy is high in case of the weak electrolytes, which is the heavy metals. Heavy metals basically are having high amount of charge, high large number of protons, which causes to increase the charge over them, due to which nuclear force is increased and their diameter, I mean their atomic radius is decreased, smaller size is there. As a result of this smaller size, it causes to decrease their volume, increase their density, as a result of which they are less reactive, more stable, as a result of which when they tend to form the bonding, they as they are less reactive, more stable, they are having high amount of lattice energy, such that during their dissociation, instead of you instead of releasing energy during their dissociation, because of their more stability, they will require additional amount of energy in order to dissociate themselves into the ions in the solution, such that energy will be transferred, enthalpy will be transferred from the surrounding to the system, which is the lattice, the ionic lattice, in order to dissociate into its ions. So at that process, when there will be uh, a let's suppose there will be heavy metals, or weak electrolytes, or a smaller size at metal atoms, then there would be endothermic reaction. And endothermic reaction would be occurring, which means energy will be taken from the surrounding, which is a solvent, into the solute. And the sign would be positive. When it comes to opposite of it, heavy light metal atoms such as group 1 and 2 elements, these basically are having less number of protons, less nuclear force, due to which they are having larger size. As a result of larger size, they have less density, high volume, due to which they are more reactive and less stabilized, due to which they tend to dissociate into ions more readily. As a result of which, when they tend to dissociate into ions more readily, they have less amount of lattice energy. As there is less amount of lattice energy, they will tend to release energy instead of utilizing energy. As they have less amount of lattice energy, they tend to release energy from their bonding. And as they have less amount of lattice energy, they tend to release energy from their bonding into the surrounding, as a result of which the reaction which would be occurring would be an exothermic reaction. That would be negative sign, denoted by negative sign, which means heat will be transferred from the system to the surrounding, which means the lattice energy will be released in case of the the strong electrolyte or light metals. Likewise, if we talk about other phenomena in the corrosion and corrosion chapter which we previously studied, light metals are more reactive, due to which they corrode highly, as compared to heavy metals, which corrode less, which are less reactive, which corrode less. Reason behind it is again their nuclear force. The nuclear force in heavy metals is high, and nuclear force in light metals is low. This is a reason. And apart from that, um, when it comes to some other characteristics of solutions, there are nine types of solutions. One is first, nine types of solution there: solute, solute, solute. First and foremost, we need to understand the interactions. There are three types of main forces of interactions in solution: solute, 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 solvent, and solvent, solvent. Whenever the solvent solvent interaction and whenever the solute solvent interaction is greater than the solute when the solute solvent interaction is greater than or equal to the solute solute and solvent solvent interaction, it causes to produce a solution. And if it is not greater than that, then there will be no solution forming, right? And one more thing, there are nine types of solutions over here, which are known as solid. 9 types of solutions are there actually: solute, 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 solvent. Sorry, once again, it's a mistake. It's solid. I was just solid, liquid, solid, 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 gas. Then three solutions of liquid, 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 solid, liquid, gas, 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 liquid, gas, solid. These are the 9 solutions. Now solid solution is the one in which solid is a solvent and solid is also a solute. Now in this case, example of this is alloy. In alloy, let's suppose copper and aurum. Copper aurum solution, in that aurum is the solvent and copper is the solid because aurum is present in large quantity. After the solid liquid, salt water is an example. Solid is the solute and liquid is the solvent. So it is, liquid is the, I mean, the water is the solvent and salt is the solution. Salt is the solute. Solid gas having example of dust particles in air. Dust particles are solute and the air is the solvent, which is the gas. Liquid having examples of two liquids combined together, milk and water. In that case, milk is the solute, milk is the solvent, and water is the solute. Milk is the solvent, water is the solute. After that, liquid and solid, it is in which liquid is the solute and solid is the solvent. Such that if we talk about butter, cheese, cheese amalgam, in which solid is the solvent and liquid is the solute. After that, when it comes to liquid and gas, in that case, gas would be considered as a solvent and liquid as a solute. So example of this is water vapors in air. Water vapors in air is a solution of liquid gas. Gas solution, air is a mixture in which 79% of nitrogen is present, which is a solvent, and the rest of the gases are solute. And when it comes to other part, gas liquid, in gas liquid solution, we are having a good example of river water and sea water. In river water, sea water, liquid is the solvent, the water is the sea water is the solvent, and the water vapors which are being the oxygen which is being captured by the water molecules inside the sea is a gas which is acting as a solute. So this is gas, solid, liquid example. Gas solid example is having example of solid and gas. Solid basically acts as standard hydrogen electrode, in which the platinum acts as the solvent, and gas which is being pulled over it would be the solute. So this is about it. And hydrophobic, hydrophilic molecules. Hydrophilic are those which love water, which interact and are miscible with water, and hydrophobic are those which are immiscible with water. Those which are miscible with water are basically known as the solute. Basically, those which are miscible with water are known as hydrophilic, and those which are not miscible with water are known as hydrophobic. The reason behind hydrophilic is that hydrophilic form hydrogen bonds with water because they themselves have hydrogen bond, while hydrophobic compounds do not form hydrogen bonds with water because they do not have that amount of their high amount of attractive forces which they can allow them to overcome the hydrogen bonding of water and cause to form a hydrogen bonding between them and water. So this is the reason. After that, some other characteristics about um, uh, you know m- miscible liquids, miscibility of the liquids. So before discussing that, we need to understand what is dissolution. Dissolution is basically the capability of a solution to a solid to dissolve into the solvent, and the rate through which the solution is dissolved into the solvent is known as the dissolving rate. Dissolving rate, and that dissolving rate is the rate at which the solute dissolves into the solvent, and that dissolving rate is directly proportional to the particles is inversely proportional to the particle size. As we have previously discussed, that if particle size is increased, then lattice energy would be increased. So particle size inversely proportional to particle size. Temperature directly proportional to temperature. Directly proportional to stirring. as well as and directly proportional to solute concentration. Sorry, inversely proportional to solute concentration, because if solute concentration is increased, then more amount of solute will have less amount of space in order to dissociate within ions. So in that case, this is the condition. And one more thing I'd like to highlight over is about the miscibility. So there are three types of solution based on miscibility: complete miscible solution, completely miscible solution, partially miscible solution, and incompletely miscible solution. Complete miscible solutions are those in which the principle like dissolve like is occurring. Principle of like dissolve like, such that if there is water, then water is able to dissolve with solutions which have hydrogen bonding, such as methanol, ethanol, and these are having hydrogen bonding. So methanol and ethanol can be dissolved in water. Likewise, oil, cyclohexane can be dissolved in ether because they have London dispersion forces. Now, reason behind it is that hydrogen, water, as well as methanol, ethanol are having hydrogen bonding, such that when methanol and water, let's suppose, react together, they cause to produce a hydrogen bonding in the form of a solute-solvent interaction, which is greater than the solute-solute interaction, as well as the solvent-solvent interaction, i.e. water-water interaction, and methanol-methanol interaction, due to which the hydrogen bonding is created, which is an able to be produced in order to cause the process of formation of stronger solute-solvent interaction. When it comes to the oil and cyclohexane, these are those molecules which are basically having um, London dispersion forces, such that when they cause to create London dispersion forces, they tend to overcome their solute-solute and solvent-solvent interaction and produce solute-solvent interaction, which is either equal to uh, their solute-solvent interaction or greater than their solute-solute and solvent-solvent interaction. After that, when it comes to partially immiscible water, liquid in partially miscible liquids, there are the two solute and solvent which partially mix with each other by forming two layers of supersaturated solution. Two layers of supersaturated solution, and each layer of supersaturated solution contains one of the solute as the one of the compound as the solute, and one of the other liquid as a solvent. Example of this system is phenol water system, aniline water system, aniline and hexane system, and nicotine water system, right? Nicotine water system. When it comes to phenol water system, the upper layer is made up of 5% of phenol in water, and downward layer is made up of 30% water in phenol. So in that case, when we increase the temperature, this type of layering is known as conjugated solution. Conjugated solution, right? Conjugated solution, which basically over here, uh, if we are increasing the temperature, if we increase the temperature, then the kinetic energy of molecules is increased, and at that moment molecules will turn from their supersaturated state to saturated state. They will form saturated solution, such that phenol will move from higher concentration to lower concentration, from lower layer to upper layer, and water will move from upper layer to lower layer as per its concentration gradient, due to which a conjugated solution will be now gradually dissolved, and at 65.9 centigrade, 65.9 centigrade, both of the layers will contain 34% of phenol and 66% of water. So at that moment, both of the layers will have equal concentrations, due to which they will be identical. And above heating on 60 above 65.9 centigrade, the solutions, the two conjugated solutions will now be submerged into a single solution, which would be the saturated solution, and that would be considered as complete miscibility. Now, the temperature at which the two conjugated solutions are submerged in order to produce one saturated solution, is known as the upper consolute temperature, upper consolute temperature, or critical solution temperature. Critical solution temperature. Now, the critical solution temperature for phenol water is 65.9 centigrade with 34% phenol. For aniline water, it is 167 centigrade with 15% water. For aniline and hexane, it is 59.6 centigrade with 52% aniline. So these are the concentrations. That's all about resistivity. Hopefully, we'll meet again.